luckily I had a bit of a break there because of some filming technicalities, and my heart rate has decreased enormously. It's only 60 now, and I've been pedalling along 59, 58, so I'm generally reasonably fit and healthy. So my cardiac output is quite high because I've trained quite a lot. My heart's quite big, so my stroke volume is quite large, so my heart rate can be quite low even though I'm respiring and creating lots of energy to ride my bike. So if I got asked a question, roll it back up, about if I had something sort of that would reduce my cardiac output, if I had something like a reduced heart rate, or my stroke volume was quite small because I wasn't very fit or healthy, then what would happen to my muscles? Well, if I had reduced cardiac output, I'd have less oxygen flowing around my body, less blood, and less oxygen blood leaving the heart, so I'd have less oxygen and less glucose digested from my digestive system. I'd have less aerobic respiration, which would lead to less energy. So, less waste product will be removed, so less carbon dioxide, so we have to respire more anaerobically. Now, if I was going to do some vigorous respiration, I'd change my gears. I'm going to go up into a higher gear, so it's more difficult, so I need more energy. So I'm going to start to respire really vigorously, it's like a 100-metre runner. If I was Paula Radcliffe doing a marathon, I would never respire anaerobically because I can't do it for 3 hours because I make too much lactic acid and go past my lactate threshold. So, if I did that, I'd have loads of lactic acid, I'd get cramp, I'd get super tired, my muscles wouldn't contract very well, and I would have to give up. So, if you've got a 6-mark question about how your muscles would be affected if you had a reduced cardiac output, you'd have to say something like that. Right, I'm going to reduce the energy requirements, but there's one last thing I need to show you, which is how to measure your lung capacity, because you might ask about this. Now, I'm lucky, lung capacity is partially genetic and how much you train. You can increase the size of your heart and you can increase the size of your lungs, you can increase how efficient your muscles work, you can change your muscle type from fast twitch to slow twitch, but you can't do it the other way around. And when I was at Loughborough, I did lots of training studies and they took muscle samples as I was running actually and looked at lactate threshold, blood percentages and all that kind of stuff. But this is a very simple lung volume meter. So all you have to do, and it's really long, it's all rolled up, I'm going to stop pedalling, heart rate's on 104, so I'm probably still respiring aerobically. I'm just going to blow into it. And then you clamp down, and all you have to do, and I'm not going to do a very good job with this because I'm sat on my bike, is roll it from this end and you're trying to get all of the volume of air into the end of the bag. Now I did this earlier when I hadn't been exercising and I was just sat before and I got 4.5. But if you look at that now, the lung volume that I've got there was about 3.5 litres, which if you think about it, it's quite big. It was 4.5 litres before I started exercising, so it does change obviously. But just quickly to recap, respiration is what keeps you alive, not breathing, okay? It's the opposite of photosynthesis, so we use glucose and oxygen to make carbon dioxide and water. Plants take in carbon dioxide and water and make glucose and oxygen that we need. Normally you respire aerobically. Vigorous exercise you make anaerobic respiration, which you create lactic acid. Plants do respire anaerobically, but that makes ethanol rather than lactic acid. We've looked at cardiac output, stroke volume, heart rate, arteries, veins and capillaries. Now I've done my artery in purple because it's deoxygenated blood. Veins, deoxygenated blood and your artery. We've looked at the blood flow through your heart, very important. You do need to know the names of the your circulatory system. So the vena cava is the biggest vein that goes in with your deoxygenated blood. Right artery, atrium, right ventricle, you have to imagine it's stuck inside you. Then it comes out the pulmonary artery to the lungs, becomes oxygenated, comes back down here in the pulmonary vein. Remember, the left-hand side of your heart is much thicker than the right-hand side because it's about 3 times thicker, so it has to pump all the blood to go around your aorta, all around your body. I hope you learned lots about respiration. I'm really looking forward to seeing you all in September, and we can link all the sciences together with your gears and your chemistry, your exothermic reaction, and hopefully we'll all do brilliantly on your GCSEs. Well done this year.
Say bye.
Bye.